So we do have a compound interest formula being the first one here. An initial amount of $10,000 is invested in a certificate of deposit with a 5.9% annual interest rate, APR. Yeah. How long will it take for the investment to double if the interest is compounded monthly? Okay. So we see this as compounded monthly. And just so you know, doubling $10,000 would make the final amount $20,000. Sometimes students overlook little factoids like that. I mean, we do have an initial amount here. Tell you with all due respect, I mean, if I had an initial amount of $1, it would take the same amount of time to double that as it would take $10,000 and double that to 20,000. That's how exponential growth and decays work. You know, it doesn't matter what the initial amount is. We're talking about a proportion description here, and proportions are what's being changed here. So, so I would set up all the information based off of that. I'm looking for t, which is the amount of time. So 20,000 would be the final amount. 10,000 would be the initial amount. 1 plus 0.059 would be the interest rate as a decimal only. It is compounded monthly, so there's 12 months in a year, so n is 12, and that's into both positions there. I'm trying to solve for t. Divide both sides by 1,000. I work out that mess inside there. I do get a repeating decimal. You know, I make use of my calculator's memory functions to keep that decimal in there because it is easier to work with the decimal here because I already have decimals involved. Um, I could also just raise that to the 12th power right away, but it makes it even a nastier decimal result. So, but I would use, in either case, I would certainly use the memory features of my calculator to keep all the decimal points it actually shows, and plus the others it has in its stored in its memory that it's not being shown on the screen will also be known as well. So, and be part of the calculation. Now I'm going to apply a natural log to both sides. Now it doesn't matter what kind of log I apply to both sides. It could be a log base 10 too. It doesn't matter. The whole reason is if I put those logarithms in, I'm going to have the natural log of 2 times equaling the natural log of 1.004916 repeating to the 12t power. But again, by the exponent rule for logarithms, that exponent of 12t can be brought down and made a multiplication. Now what I have is natural log 2 and natural log 1.004916 repeating being numbers, and I'm going to treat them as numbers. So I would divide both sides by that, and then I would divide both sides by 12, and I would get about 11.78 years. Now it says how long will it take for the investment to double if it's compounded continuously. Now it has the word continuously, so I have to use the different formula. So here 20,000 is going to equal 10,000 times e to the 0.059t. A little bit more of a simplistic calculation here because now when I use natural log, it's going to clear out the e on the one side. So I'm going to have 0.059t equaling the natural log 2. T is going to be the natural log 2 over 0.059, which is 11.75 years. Not a big difference, but if you remember, you know, when I compounded continuously versus monthly, if you looked at that experiment we did when we were discussing the evolution of what number became E, there wasn't a whole lot of final amount differences between monthly and continuously either. So I'm not expecting a huge difference in time here between the two. If I was looking at annually versus continuously, that's a different story. But monthly and continuously, not so much of a difference.